Pluto is a far-off and puzzling diminutive planet that was once an individual member of our nearby planetary system's planetary family. However, ongoing frightening declarations by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a stunning disclosure. They recommend that this frigid world is on a potential crash course with Neptune. Yet how might this occur, and what might be the outcomes of such a gigantic event? Are we seeing a unique cosmic peculiarity, or is there something else to this approaching infinite crash? Join us as we investigate the possibilities of a Pluto-Neptune influence. Pluto, a former planet that was downgraded to a dwarf planet mostly because of its exceptional orbit, remains a subject of interest and study in the cosmic community. According to recent forecasts by leading researchers, Pluto's orbit is perilously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential risky crash between these two planets that could pose a colossal danger to Earth. How is such an event even conceivable? Pluto's orbit around the Sun is unlike any other planet in our solar system. It takes a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, veering off substantially from the near-circular orbits of the major planets. What makes Pluto's orbit even more peculiar is its tilt, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This tilt and elliptical nature add layers of complexity to its orbital pattern. One of the most interesting aspects of Pluto's orbit is its convergence with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This leads to the natural question: why hasn't Pluto slammed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets, whose orbits lie relatively near the ecliptic plane, Pluto's orbit stood out due to its steep tilt and elliptical shape. The mystery grew with the realization that Pluto's orbit actually crosses Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space is about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all work together in a complicated way. The terms alpha libration and scope libration, along with the VZK oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In the case of Pluto and Neptune, this term means that when Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from impacting one another. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned significantly above their orbital plane, adding an extra layer of protection from potential crashes. Another significant aspect in this situation is the VZK oscillation, named after three researchers, Bond, Zippel, Leo, and Kai, who studied how objects move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling influences how they move. In Pluto's case, the VZK oscillation helps us understand why its orbit around the Sun is so unusual. Although Pluto's orbit seems erratic, the oscillation helps keep it moving smoothly for billions of years. The VZK oscillation shows that, even though things in space may seem chaotic and random, some patterns and rules keep everything in place. All of these factors help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or lose its way. This three-body problem helps us understand how orbits change due to the way space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and distant worlds and their stars. Mathematical simulations in the late 1980s revealed that, despite these stable properties, Pluto's orbit is actually turbulent, with small deviations in initial conditions leading to significant differences over thousands of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos under control. Recent computer tests have helped us understand how the giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a special connection with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This connection helps keep Pluto's orbit stable. But Neptune isn't the only one helping. Jupiter's gravity also plays a huge role in stabilizing Pluto's orbit, and Saturn helps as well. These tests show that Jupiter's gravity alone is powerful enough to ensure Pluto stays on a steady course for a truly significant period of time, even billions of years. So, it seems Neptune, Jupiter, and Saturn are working together to make sure Pluto continues to move safely through space without running into trouble. These phenomena are fundamental in the context of the universe for maintaining the order and consistency of celestial movements. Without these mechanisms, the solar system, as we know it, would be a much more chaotic and unpredictable place. Bodies like Pluto could potentially crash into others or be ejected from their stable orbits, leading to a cascading effect on other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is crucial. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of ongoing observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often leads us to confront the erratic nature of celestial bodies, and Pluto's orbit is a great example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. This means that even slight variations in the dwarf planet's position or speed can dramatically shift its long-term course within the vast reaches of our solar system. Pluto occupies a unique place that challenges our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has undergone extensive study, leading to significant revelations about its composition and behavior. One of the most fascinating aspects of Pluto is its surface, which is a complex mosaic of ice, rock, and various compounds. NASA's New Horizons mission, which flew by Pluto in July 2015, provided extraordinary data about this distant world. The surface of Pluto is characterized by vast fields, towering mountains, and deep valleys. One of the most striking features is Sputnik Planitia, an immense heart-shaped plain made almost entirely of nitrogen ice. This region showcases a diverse array of geological features, including massive ice shelves and what appear to be flowing ice sheets. The presence of these features suggests that Pluto might still be geologically active, despite its great distance from the Sun and low temperatures. Another intriguing aspect of Pluto is its atmosphere, composed mainly of nitrogen with traces of methane and carbon monoxide. Pluto's atmosphere is thin, but it exhibits fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the complex relationship between Pluto and its environment. During its closest approach to the Sun, some of the atmospheric gases may freeze out onto the surface, while as it moves farther away, these gases can sublimate back into the atmosphere. The interaction between Pluto and its largest moon, Charon, also adds complexity to the system. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that the two bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply rotating around Charon. This unique relationship contributes to the complex gravitational dynamics in the region, affecting the orbits of other objects in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to many other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, giving scientists a glimpse into its formation. Pluto's orbital characteristics could offer insights into the motion patterns of these distant objects, suggesting that interactions with larger planets may have played a pivotal role in shaping their current orbits. One of the key implications of understanding Pluto's orbital elements is the potential impact on our understanding of the solar system's evolution. The gravitational effects from nearby giant planets like Jupiter and Neptune can modify the trajectories of smaller bodies, including those in the Kuiper belt. Such interactions can result in shifts in orbits, potentially leading to collisions or ejections from the solar system. As researchers continue to explore the details of these interactions, they may uncover broader patterns that govern the behavior of celestial bodies throughout the universe. The study of Pluto also raises philosophical questions about classification in astronomy. The decision to reclassify Pluto as a dwarf planet in 2006 was controversial, sparking debates about what constitutes a planet. The International Astronomical Union's definition focused on criteria like orbital dominance and size, leaving many to ponder the implications of such classifications. This ongoing debate reflects our evolving understanding of the universe and underscores the need for a flexible approach to categorizing celestial bodies. Additionally, the potential for future exploration of Pluto and the Kuiper belt remains an exciting frontier. With advances in technology and mission planning, scientists are envisioning sending additional spacecraft to study not only Pluto but also other distant objects that share its orbital characteristics. Such missions could provide invaluable data about the primordial materials that formed our solar system, potentially shedding light on the origins of life on Earth. The study of exoplanets, or planets outside our solar system, is another fascinating area of research that intersects with our understanding of Pluto. As astronomers discover an increasing number of exoplanets, particularly those in the habitable zones of their stars, the lessons learned from studying our own solar system can inform theories about planetary formation and habitability. The conditions that allow for stable orbits, atmospheric retention, and surface activity could offer insights into the potential for life elsewhere in the universe. Finally, public interest in Pluto has persisted, fueled by its mysterious status and the stunning images sent back by the New Horizons mission. The dwarf planet has captured the imagination of people worldwide, inspiring a renewed appreciation for the vastness of space and our place within it. As we continue to unravel the mysteries of Pluto and the celestial bodies that share its region of space, we are reminded of the immense wonders that the universe has to offer. Do Pluto's unique attributes extend beyond its physical properties and orbit? It also serves as a crucial case study for understanding planetary development and the dynamics of celestial bodies. The formation of Pluto is believed to have occurred in the early solar system, alongside other Kuiper belt objects. Studying its composition can shed light on the conditions prevailing during the solar system's infancy, possibly illuminating theories about the development of terrestrial planets, including Earth. Ongoing research suggests that Pluto may have a subsurface ocean, a discovery that could alter our understanding of its geology and potential for hosting life. Data from the New Horizons mission revealed that some regions of Pluto's surface, such as the icy mountains, may be composed of water ice, which behaves differently from typical rock under low temperatures. This finding invites further investigation into the possibility of liquid water existing beneath its frozen exterior, raising intriguing questions about the potential for life even under such extreme conditions. Furthermore, Pluto's interaction with its environment provides valuable insights into planetary science. The seasonal changes in its thin atmosphere offer a natural laboratory for studying atmospheric processes on a planetary scale. Scientists are particularly interested in how the interaction between solar radiation and the surface can give rise to complex weather patterns, similar to those observed on larger planets. The importance of continued surveillance of Pluto and other similar celestial bodies cannot be overstated. As more missions are planned, such as those targeting the farther reaches of the Kuiper belt, we can expect an abundance of new data that challenges existing theories and expands our understanding of planetary science. Each new discovery adds another piece to the puzzle of our solar system's history and the processes that govern its evolution. Through these investigations, Pluto remains a symbol of the unrelenting quest for knowledge about our universe, inviting both scientists and enthusiasts alike to ponder the mysteries that lie beyond our earthly domain.